Hello, this is Mr. Henry, and welcome to Lesson 3.4, Properties of Similar Figures. The essential question says, how do I identify properties of similar figures? In the past few lessons, we've talked about dilations and how they make similar figures. In this lesson, we're going to start talking more specifically about the similar figures and less about the dilations, and figure out, well, what exactly is similar figures and what are some properties and ways we can identify if figures are similar. So the warm-up question asks, what do you know about similar figures? Take a couple seconds and jot down some notes. When you're ready to continue, hit play and we'll go through them together. So you might have said some things like, well, similar figures come from dilations, which is true. You might have said that similar figures are proportional, which is true. And there's a variety of other things you could have said about similar figures, and we'll probably be talking about some of them in this lesson. So let's jump right in. We have two vocabulary words, and you see they're both the same. Both are the word similar, but we have one definition that's a little bit better and one that's not quite as good. This definition is not very good. It says same shape, different size. You might have heard that before. The problem with that is it's not very specific. When it says same shape, are we talking about any two triangles are the same? Are those two similar? They're both triangles. They're both isosceles triangles. They're both isosceles acute triangles. So they're the same shape, but they're different sizes. So are they similar? And the answer there would be no. Those two are not similar. So we need a little bit better of a definition. So here we have similar figures are two shapes that are proportional and can be shown using a dilation and a rigid transformation like rotation, reflection, and translation. So these similar figures happen if you have a shape. So let me get here a shape here. And if I would take this and clone it, this shape is similar to the larger shape. If I rotate it, it's still similar. If I translate it, it's still similar. If I would flip it around, it's still similar. So all that makes something similar is that it has a dilation and some other transformation that doesn't change the shape, any of these rigid transformations we talked about in the previous module. So let's see here. I have three triangles, and the directions ask us to identify which shapes are similar. And it says be sure to explain how you know this is the correct answer. So just by glancing at these, I bet pretty much everybody can figure out which two are similar just from the information shown. Hopefully, you said triangles LMN and RST are similar. Because just with the information shown, we have angles. Well, this angle is the same as this angle. This angle is the same as its corresponding angle. The 90-degree angles are the same. So these two triangles have the exact same angle measures. They are similar. Similar triangles or similar figures, don't even have to be triangles, always have the exact same angle measures. So we can tell right there, LMN and RST are similar, because they have the same angle measures. Their corresponding angles are congruent. They are the same measure. Example B. We have three triangles here and a little cramped. There we go. So I have DEF, JKL, and XYZ. And I want to know which of these shapes are similar. So the first thing I'm going to do is remind you that similar figures are proportional. So if similar figures are proportional, we can use a proportion to determine if they are similar. Because if we set up a proportion and we cross multiply and it doesn't work out to something good, then the shapes aren't similar. Example. So here we're going to compare triangles. So I'm going to start with comparing these two, DEF and JKL. So I set up a proportion. So it doesn't matter which side you pick for your proportion. But let me be specific. So if I've just picked this side randomly from DEF, sure, 12 goes here. What matters is that this side in your proportion is the corresponding side of your triangle. So 12 corresponds to 18. I'm going to pick another random side of this triangle. I'm going to use 6. 6 corresponds to 7. So you can pick any random sides of your triangle, but for the other part of your proportion, make sure you're using your corresponding sides. Now, let's cross multiply. So I take 6 times 18 is 108. Yep. 7 times by 12 is 84. So those are not similar. Because 84 does not equal 108. That did not work out. So DEF and JKL are not similar. So now I'm going to try my next pair. So it wasn't those two. Maybe it is DEF and XYZ. So I'm comparing this first one and this third one. Same thing. If they're similar, they should be proportional. I use pretty much the same proportions. I'm going to use the same sets of sides. So I'm going to say 12 over 18. I'm sorry, 12 corresponds to 18, and 6 corresponds to 9. And if I cross multiply here, 9 times 12 is 108. 6 times 18 is 108. Those are similar. Because when I cross multiplied, my proportion worked out. I got 108 equals 108. So those two shapes are similar because they are in proportion. You can use proportions and cross multiplying to check to see if shapes are similar, if they are in proportion. Now, just for sake of completeness, I'm also going to check the last pair. So I'm going to check JKL and XYZ. So I'm going to check this one and this one. So let's see. Same sets of sides. I'm going to use 18 from here, and the corresponding side is 18. 7 from here, corresponding side is 9. I cross multiply. 9 times 18 is 162. 7 times 18, 126. So no, those are not similar. Okay, so we can check for similarity by using a proportion, because similar figures are proportional. Letter C. Same thing. Identify which shapes are similar. Be sure to explain how you know this is the correct answer. So, all the shapes they give me side lengths. Shapes are similar if their sides are proportional. So, we're going to use proportions. So, let's start with GFH. I'm going to compare him and him. I'm just going to kind of go this way, and that way. So G with H, or GFH and XWXY. So again, you can pick any two random sides from the first triangle. So I'm going to pick 20 from here and 16 from here. And then 8 corresponds to 6. If I cross multiply, hopefully everything comes out nice. 6 times 20 is 120. 8 times 16 is 80, and 48 is 128, I think. 8 times 16, there you go, 128. So those two are not similar. So it's not these top two. So let's try WXY, WXY, and PQR. Oopsie. So my proportion says, well, I'm going to use the same sets of sides. So from WXY, I'm going to start with 16, which corresponds to 10, and 6 corresponds to 4. Cross multiplying here, 6 times 10 is 60, 4 times 16 is 64. No good. Not similar. Which hopefully means it's the last two. It would be this P, Q, R, and F, G, H. So let's see. P, Q, R, F, G, H. Proportion. Corresponding sides are 10, corresponds to 20, and 8. Oopsie, not 8. Undo. 4 corresponds to 8. Alright, let's cross multiply here. 8 times 10 is 80. 4 times 20 is 80. Yes, we found it. Those two triangles are similar because their sides are in proportion. Because the sides are in proportion, they are similar. Now, here's one for you to try. It's letter D, and it says identify which shapes are similar. Be sure to explain how you know this answer is correct. You have A, B, C, D on your paper, already filled in. What you don't have is you don't have the measures of this top triangle. So this top triangle, this angle is 30 degrees. This angle is 60 degrees. The hypotenuse of this triangle is 5 inches, the short side is 3 inches, and the other leg is 4 inches. Now, when you're checking to see which ones are similar, I'm going to tell you right now, there may be more than one correct answer. So you need to check if A is similar, and C, and B, and D. You might get one correct answer, maybe 2, maybe 3, maybe all 4. Okay, so pause the video right now, check each of the triangles to see if they're similar to the given triangle, and then when you're ready to continue, hit play, and we'll go through it together. Alright, so since this first triangle, letter A, gives us side lengths, two figures are similar if their side lengths are proportional. So I'm going to use a proportion. So I'm just going to pick some random sides. So from side A, I'm going to pick 40. And its corresponding side, the hypotenuse, would be 5. Notice, the hypotenuse of A, the hypotenuse of the given triangle. Now I'm going to use this short side of A. The shortest side is 24. And the shortest side of the given triangle is 3. If they are similar, when I cross multiply, I should get something that is equal. 3 times 40 is 120. 24 times 5 is 120. That worked. This triangle A is similar to the given triangle because the sides are in proportion. They are proportional. Okay? Letter B. Letter B, they give me angle measures. And we learned back in the first example that if your shapes are similar, their angle measures should be the same. And if you look at angle B and the given triangle, no. this and this are not the same angle measure. The corresponding angles are not the same, which means these shapes are not similar. So letter B is no. It is not similar to the given triangle. Triangle C. Again, I have angle measures. Angle measures should be congruent. So my angle measures are 30, 60, and 90. And 30, 60, 90. Those two are similar. So letter C is similar because the angle measures, or I say the corresponding angle measures, are congruent. All of the corresponding angles are the same. Lastly, to check would be letter D. So letter D, they give me side lengths, so I'm going to use proportions because similar figures are proportional. Small little typo here, forgot to fix this one. It should be a 26. It should be right on your paper. There, 26 is better. So, let's plug in some sides. So I'm going to use the same couple of sides. I'm going to use the hypotenuse here. Corresponds to the hypotenuse here, which is 5. The shortest side of letter D is 16. And the shortest side of the given triangle is 3. Alright, let's see what happens when I cross multiply. 16 times 5 is 90. And 3 times by 26, let's check that out. 3 times 26 is 78. So this letter D is not similar to the given triangle because the side lengths were not proportional. So this has been the computational part of this lesson, where we just do some problems without any words really. It's just straight up giving you problems. But you've learned everything you need to learn. Side lengths should be proportional. Angle measures should be the same, congruent. Now we're just going to take those same ideas and use them in some word problems, and we're done. So example 2a says James drew a triangle that has dimensions 16 inches, 10 inches, and 20 inches. Janet drew a triangle that is similar, except her shortest side is only 6 inches. What scale factor would be used to show that these triangles are similar? So, if you remember, similar figures come from dilations. Dilations have scale factors. Therefore, similar figures also have this scale factor. There's a relationship between the size of the one and the size of the other. We said here that these two are similar. Well, look, if you take this number times by 8, you get that number. The corresponding sides are just bigger by 8 times. That would be the scale factor here. Well, we need to do the same thing, but in this problem. We need to find the scale factor. So, from James's shortest side to Janet's shortest side, there would be a start of our scale factor, the ratio. Now, this is going from Janet to James. And I just need to simplify this. And so if I divide top and bottom here by 2, I get 5 over 3. And that doesn't simplify any 4. So that means that James's triangle is 5/3 bigger than Janet's triangle. That's a scale factor that relates James's triangle to Janet's triangle. So if I took all of the side lengths of James, this 16, this 10, and this 20, and if I would multiply each of them by 5/3, that would tell me how big, I'm sorry, the other way around. If I took all of Janet's sides and I multiplied it by 5/3, that would give me how big James's sides are. So 6 times by 5/3 would give me 10. Okay? If you take the other two sides of Janet's triangle and multiply by 5/3, you'd get the 16 and the 20. Because the shapes are similar, they all have a similar scale factor. So a scale factor is nothing more than a ratio comparing the two figures. Letter B. It says triangle ABC is similar to triangle LMN. Okay, so if you need to draw a picture, sure. ABC, LMN. Alright, angle A is 38 degrees. Angle B is 19 degrees. Using this information, is triangle LMN acute, right, or obtuse? So we know a couple pieces of information here. We don't know anything about this LMN except that it's similar. Well, similar figures, the angles, I should say, are the same. So this, if angle A corresponds to angle L, then L would also be 38 degrees. If angle B is 19 and corresponds to angle M, then M is also 19. All right. But in order to figure out if this is an acute, right, or obtuse triangle, we need to know all of the angles. So this angle N is my missing piece. That's the thing I have to figure out right now. Let's see. I know that all of the angles of a triangle add up to 180 degrees. So L plus M plus N should equal 180. So 38 plus 19 plus this angle N, this missing thing I don't know, would equal 180. And with some simple solving equations, I'm going to add those together. 30, 40, 57 equals N, or 37 plus 57 plus N equals 180. Subtract 57 on both sides, and N equals, Mr. Calculator says, 180 minus 57 is 123. So this angle N is 123 degrees. Now that I know how big each angle is of this triangle, I can tell you if it's right, acute, or obtuse. And the answer is, it's obtuse. You look at the biggest angle of the triangle. If the biggest angle is obtuse, it's an obtuse triangle. If the biggest angle is a right angle, a 90, then it would be a right triangle. If the biggest angle of a triangle is acute, if they're all like 60, then it would be acute. But in this problem, LMN is obtuse. So this used similar figures, knowing that the corresponding angles are the same, and then a little bit of background knowledge knowing that all the angles of a triangle add up to 180 degrees. Here's letter C for you to try. It says, a group of 4 students was each asked to construct a triangle with angles that measure 42 degrees, 74 degrees, and 64 degrees. If each student makes their own triangle for homework, can we determine if they will all be congruent triangles, or how about similar triangles? So maybe you want to make some sketches on your paper if you need to, but answer this question, pause the video. When you're ready to continue, hit play, and we'll go through it together. All right, so if 4 students all made a triangle, and it gave us the angle measures, can we say if all of the triangles will be congruent or similar? Well, congruent means that they're exactly the same. All the sides are the same, all the angles are the same. It's like a clone of one another. That would be like a rigid transformation. So those two, I literally just hit clone. Those two triangles are congruent. I don't believe they would. Because there's nothing here that says that the side lengths have to be the same. All it says is the angles have to be the same. So this triangle, if I shrink it down, it's still similar. The angles would all be the same, but the side lengths would be different. So, no, they would not have to be congruent. For each, could we determine if they'll be congruent? The answer is no. They will not all be congruent because one triangle might be bigger or smaller, even though they all have the same angle measures. But what about similar? Would they all be similar triangles? The answer there is yes. They would all be similar because if you have 4 triangles, and I know I'm getting sloppy now, but if you have 4 triangles and they all have the exact same angle measures, 60 or 74, 42, 64, and it's the same for each of them, then they would be congruent. They would be similar. Similar triangles have the same angle measures. So if you have 2 triangles that have the exact same angle measures, they will be similar. They will be proportional. They are just dilations of one another. Letter D. Lindsay drew a triangle on a balloon. The triangle had dimensions 24 millimeters, 44 millimeters, and 38 millimeters. She then inflated the balloon and measured the dimensions to be 65, 100, and 81. Is the triangle on the inflated balloon similar to the triangle on the non-inflated balloon? Go ahead, pause the video, and try it out. Okay, so essentially we've got 2 triangles. We've got 24, 40, and 38, and another bigger triangle with 65, 100, and 81. So this is the one after the balloon has been inflated, and this is after the balloon has been, well, non-inflated or deflated. And we want to know if these 2 triangles are similar. Well, the way we did that before is proportion. It's going to be the same. So we take a proportion, boom, boom. I'm going to pick a couple sides at random. I'm going to use those 2. Why not? So 24 corresponds to 65. 38 corresponds to 81. And if I cross multiply, and if I get the same thing on both sides, then they are similar. So we're going to take 81 times by 24 equals 1,944. On the other side, we take 38 times by 64 equals 2,432. So the answer here is, in this case, no. Those 2 triangles may not be exactly in proportion. They would not be similar. Maybe one part of the balloon inflated more than another part of the balloon, or something along those measures. So those triangles are not similar. So in your own words, how can you tell if 2 shapes are similar? Go ahead, pause the video, answer that question, and then we'll go through it together. And I have here, you can tell if 2 shapes are similar if the corresponding angles are congruent. And you can tell if the shapes are similar if the corresponding sides are proportional. This has been lesson 3.4. Thank you for watching.